everybody, and welcome back to Echo Live, coming to you from the Michigan Science Center. My name is Anna, and today we are going to be talking about air everywhere. So we've been doing a few demonstrations on Echo Live so far about our vacuum chamber, talking about what happens to objects when we actually remove air from a system. To change it up just a little bit, today we're actually going to be talking about the power of air, since air is all around us all the time. Now, air here on Earth is pretty special, and we'll get to the composition of air as we move through this program. Now, if you're watching on Facebook Live or through Zoom, now would be a great time to introduce yourself in the chat. So let us know you're here. That chat feature is the way that you'll communicate with me during this program. That's how you can answer all the questions that I ask of you, and how you can also ask questions that you'd like me to answer here from the studio. So go ahead and introduce yourself in the chat. And one more reminder before we get started with today's presentation, that we did launch a poll yesterday asking for your input about what time we should host Echo Live. So make sure that you respond to the poll or tell us through Facebook Messenger or another method if you have thoughts about the time we should host our Echo Live programs here on Facebook and through Zoom. So hi, everybody. I'm seeing lots of comments coming in, lots of returning faces that we see here every weekday, lots of new faces as well. So welcome, everybody. So today we're talking about the power of air. And what better place to start than with a demonstration using air and air pressure that you can try at home. So I have this demonstration right here on this orange tray. This is a demonstration that you can try at home to show that there is air and air pressure around us all the time. For this demonstration, you'll only need a few materials. You'll need a glass of water or a container of water of some sort. Mason jars work great for this demonstration, but any kind of container that has a lid with a lip on it would be great. We'll also need another of those nylon stockings. So if you tried our really gross burger demonstration yesterday from Echo Live, you might have one of these laying around, a rubber band, and some sort of laminated or kind of water resistant card. A playing card could work depending on the size of your vessel. And we're going to walk you through this experiment right here in the studio. Now, to demonstrate how this relates to air pressure, we have to first set up our experiment. So before I started the program, I've already filled our jar about 3/4 of the way full with water. So we can see that there's water here inside the jar. We're then going to take our stocking, and you want to choose a flat part of the stocking, so not a part that has a seam or a sewn part on it, and just kind of stretch it over the lid of your container. You'll want to secure it with a rubber band. And then we can go ahead and we can try our first air pressure experiment. So I'm going to take my laminated card, something that's not going to get soaked through by the water. So I've just laminated a piece of paper. You might have something similar laying around your house that you could use. And you're just going to place it over the top of the jar. Now, what we're going to do is we're actually going to invert this jar. I mean, we're going to flip it upside down and watch what happens. So we're just going to take it, put your hand flat on top of the laminated card, flip it over. And then our next step is going to be to let go of the card. So if you have a guess about what might happen when I let go of the card, go ahead and put that in the chat. Now remember that this cup was about 3/4 of the way full of water. And water does have mass, meaning that it does have gravity pulling down on it, right? And now that our cup is upside down, the open side is facing down here. All right, so let's go ahead. We're actually just going to remove our bottom hand here from the system. Oh, no. Now, even though my card fell, you might be able to tell that there is still water inside our container. So we've kept our water inside our container, even though we don't have the card. Now, the card was important when we flipped it over just to kind of hold the water inside. But the water is remaining inside our vessel thanks to air pressure. There's a little bit of air inside the cup, but there's a whole lot of air outside the cup that's actually pushing up. Now, if we try to do this again, I think my card might have been a little wet. If we kind of wiggle this back and forth, we can actually get our card to stick. So there are some other factors at play here. Water has some very interesting chemical properties. Water molecules really, really like to stick to each other. We call that cohesion with a C. So cohesion means that those water molecules want to stick together. So they form somewhat of a barrier that the water or that the air is actually pushing up on. Now they also have what we call adhesion, meaning they like to stick to other things as well. So they're adhering to the stocking, they're cohering to each other, and that forms a barrier for the air all around us to push up on. Now, if we create an imbalance in water pressure, either by disrupting this barrier, by shaking the jar, or by changing the air pressure, the direction of the air pressure by maybe tilting it, you notice that we make a huge mess. So if you are going to try this experiment at home, I highly recommend trying it in either over a sink, over a tray like I've done, or maybe even go outside and try this one outside in the nice, beautiful weather that I know we're at least having here in Michigan today. So that is talking about the power of air that's all around us. In general, we say that there are 14.7 pounds per square inch of air pushing on every inch of every object here on Earth. So 14.7 pounds per square inch of air pressure all the time. That was great for this demonstration, but we're actually going to talk a little bit more today about how we can harness this air pressure. So not just rely on it being around us all the time, but how can we move air, or how can we use air in order to power technology or to power different objects that we use here on Earth to do work. So the first thing we're going to talk about is something called Bernoulli's principle. So I have a diagram of Bernoulli's principle here, and Bernoulli's principle simply states that in an area of high speed or moving air, we also create an area of low pressure. We're going to do a couple demonstrations that demonstrate this, but it's always good to have this on hand, or this knowledge on hand first. So at areas of high pressure, generally your air is moving at a lower speed, but where your air is moving faster, we have an area of low pressure. So we'll come back to this diagram after our first principle that demonstrates Bernoulli. So Bernoulli was the scientist that came up with Bernoulli's principle. Again, one of those scientists who really just likes to name things after themselves. I know I would if I invented something really, really cool. So we're going to be using this thing, which we call a wind bag, to demonstrate Bernoulli's principle. And the goal of a wind bag is really, really simple. A Bernoulli's bag, or a wind bag, the challenge is to blow up the entire bag, which is pretty long. It's a pretty large bag, even taller than I am if I stretch it all the way out. We want to fill up the entire bag with air with just one breath. So if we think about the size and the volume of the adult human lung, we say that it's about 6 liters of air. So if you can imagine 3 2-liter bottles that we use to hold soda, that's about the capacity of the adult human lungs. So for an adult, not even for a child. But even less than that is actually air that we can move. The amount of air that we move with every breath, we call the tidal volume. So the tidal volume is the amount that we inhale and exhale with every breath. So we don't breathe in 6 liters of air and exhale 6 liters of air with every breath. Our lungs are never completely empty. That would be really, really bad. But instead, we can only inhale and exhale about 500 milliliters of water. That's about the amount of air or water that would fit inside this beaker. So really not a huge amount. And so it's not really enough to fill this entire bag, but let's give it a shot. You know, maybe with enough yoga breaths, we can fill this entire bag with air. So I'm going to take a couple yoga breaths here, and then I'm just going to try to fill the bag entirely with one breath. Here we go. Squeezed out all the excess air, so we're not cheating. And then we'll go ahead and put in our breath in 3, 2, 1. All right, now I've trapped the air inside. Let's see how I did. And it's not bad, right? So we said that our tidal volume is about 500 milliliters. So there might have been a small amount of air that I didn't squeeze out of the bag before we started. But that's about the tidal volume of my lungs. That's about how much air I can really muster in one exhalation. So what we're going to do is we're actually going to use Bernoulli's principle in order to accomplish this challenge. So what we're going to do is, instead of holding the balloon right up flat to my face and only rely on the air from my breath to fill the bag, instead we're going to rely on Bernoulli's principle. We're going to harness the air pressure from the room all around me in order to fill up the bag. So let's squeeze out the air from this demonstration. So we're, again, making sure we're not cheating, not coming into it with an advantage. And this time I'm going to kind of just prop my end up over here. All right, I've got it propped up over there just so I can hold it level to my own head. All right, squeeze the air back out. All right, our bag is completely empty. And this time we're actually going to hold the bag about a foot away from my mouth. That's going to allow the area of low pressure, the area of high pressure, the air all around me, to rush in and follow my breath into the bag. And then we'll come back to that diagram. So let's go ahead with our Bernoulli principle air-filled bag in 3, 2, 1. We can see that we've trapped much more air inside than in our first go at the wind bag, right? So we'll trap that air inside, and let's think back to that diagram, right? When I take a breath and I push air into the bag, my breath is creating that area of high speed air, thus giving us an area of low pressure. Since I left an opening, right, if we think about the vacuum demonstrations that we've done so far, air and gases are very special that they want to fill empty spaces. So all of the air from the room, that area of high pressure, wanted to rush in, following my breath through that low pressure zone. So things always move from high pressure to low pressure. And the air from the room actually rushed in to fill the bag. So we've completed this challenge, right? Maybe not filled the bag totally, but maybe with a couple more yoga breaths, I can get this one even fully inflated. So I do see some questions popping up. This is a good time for us to pause. We'll talk a little bit more about Bernoulli's principle in just a moment here. So if you do have questions about what we've discussed so far, type them in the chat. I see that we have a couple questions coming up in our chat on Zoom. And let's remember, let's use this chat here for asking questions. I'm so glad we have so many familiar faces. It looks like on Zoom we even have some families joining in. So it's so great to see you guys. Let's use that chat to ask any questions that you might have for our presentation here. How much air flows through the world? I don't know the exact volume of our atmosphere. That's probably something we could pretty easily find out. So I'll keep an eye on that. If I can't think of an answer before the end of this program, we'll certainly reply to your comments, Stephanie. So I don't know the volume of the atmosphere here on Earth, but there's air constantly moving around us all the time. Does air float? Yes. So air is a general term. It's talking about all the different gases that make up our atmosphere here on Earth. But air is not just one type of gas. It's actually made up of several different types of gases. Now they exist in kind of a mixture, but certain portions of air or certain compositions of air are lighter than others. And so air has density just like any other kind of matter. And so some air is heavier and some air is lighter, which means it will float to the top. If you think about a balloon that's full of helium, helium is one gas that is much lighter than the composition of our atmosphere here on Earth. So helium balloons will rise and will float because their density and their weight is much less. Someone asked, did I actually do this balloon demonstration or was it special effects? I did actually do it. If you think that I had something off to the side of my camera, maybe over there, I'll throw it over the front. So I'll move my balloon this way. And we can actually do this one more time. Always down to dispel any sort of science myth. So my balloon is not hooked to anything here. We do want to prop it up a little bit, just so that it's level with my head. But I'll crouch down just a bit, and we'll try this one more time just to prove to you that it does work if you ever do want to try it. In 3, 2, 1. I think we had a little bit of a fold over my table here, but still much more than the demonstration we tried where I held the bag straight up to my face. So really, with Bernoulli's principle, we can harness a lot of air pressure in order to fill the bag. You can purchase these wind bags online if you'd like to try this yourself. They're really, really easy to come by. Just look up wind bags either on Google or on Amazon, and you can actually buy some for yourself. Will air ever run out? No, there will always be air here on Earth. What we have to worry about, right, is those certain compositional elements of the air that we need to breathe, right? So we need oxygen. Humans specifically rely on oxygen, right? And if we consume too much oxygen, right, we need a way to replenish it into the atmosphere. So things like trees and plants, right, those create oxygen, which is why it's so important for us to have plants and trees here on Earth that actually replenish the oxygen after us humans use it. Someone did notice I spilled the water, but don't worry, it's nice and absorbed into my wooden table here, so it'll be okay. Some people are asking about pollution, right? And so pollution is one of those things that can actually mix up the chemicals in our air, right? So we want a certain chemical composition of our air because it's what we've grown accustomed to for life on Earth, right? And pollution can kind of skew that. We don't want a lot of greenhouse gases in the air. We want gases that are good for us to breathe and for us to fuel all of our body processes. So we have to be careful about pollution. Great questions. Keep sending your questions in the chat so that I can keep answering them as the show goes on. But we're going to do another demonstration about Bernoulli's principle here. This is another one that you can try at home, and you probably don't need to purchase any supplies for this one. So Bernoulli's principle, not only can we use it to fill empty spaces of air, we can also use it to accomplish some type of levitation. I should preface with saying that levitation is not a scientific phenomenon. Levitation is just evidence of other scientific phenomena at play. So we might know that magnets are able to levitate, especially if you stack them and arrange their poles in a certain direction, right? We know that magnets can repel each other, which can give off something that looks like levitation. Magicians use it using kind of optical illusion, so they work with their angles to make it seem like things are levitating even if they're not. But you can accomplish levitation at home simply using a hair dryer and a small round object, something like a ping pong ball. So we're going to use Bernoulli's principle to accomplish this, right? So when I turn on the blow dryer, it's actually going to create that area of low pressure, that area of quickly moving air. If we very carefully hold our ping pong ball inside that area of low pressure, the area of high pressure will form almost a wall around the ball and kind of keep it floating on top of the hair dryer. So instead of being blown away from the hair dryer, it's actually going to stay directly on top. So let's go ahead and give this a try. So our hair dryer, right, is accomplishing levitation. I can move it around. And as long as we keep the ball kind of in that area of quickly moving air, if we keep it in that low pressure zone, the high pressure zone will trap that ping pong ball inside. So this is, again, an experiment that you can try at home. Try it with different objects. A ping pong ball works best, but if you find something else that works really well, send it to us. We'd love to hear about what you have experimented with using Bernoulli's principle. Now, if you have something even bigger, right, size maybe isn't so important. So I have something even bigger than a hair dryer. I have a leaf blower that I've taken the long tube off the end that you normally use for directing the leaf blower at your leaves on the ground. So I've taken that part off, and this can actually create an even stronger field of moving air, which means that we'll be able to levitate an even larger object, possibly an object like this planet right here. Now, tell me in the chat, do you know what planet this is? Maybe just think about it. We're going to do the same demonstration that we did with the ping pong ball using our leaf blower, and we're going to try to levitate our planet. Now, this is obviously much heavier, right? But we've got a little bit more powerful of a source of air here. Gives us even more wind power for us to try this demonstration with. Let's see. I see some people commenting that this looks like magic. It's not magic, right? This is magic that you can do at home. Magic is just something that science hasn't explained yet, which is what makes science really, really cool. So I love hearing that. I love giving you guys tips on how you can recreate this kind of magic using science. So I see a couple really awesome answers. I see that Kate was the first one to tell me that this is Jupiter. I see a couple friends on Zoom told me the same thing. I see Jenna told me it was Jupiter. So did Ava, and so did Elise. Now this is Jupiter, and you can probably tell, right, because of this thing right here. That is the great red spot that we see on Jupiter if we look at it through a pretty powerful telescope. And that's actually a storm that's been going on Jupiter for hundreds of years. So we can tell this is Jupiter because of that big red spot, or the great red spot. All right, so we're gonna go ahead and we'll try the same demonstration very, very quickly, but instead of our hairdryer, we've got our leaf blower and Jupiter. Here we go. Right now, this only works if we keep the leaf blower directed straight up, kind of keeping that area of low pressure really directed at the beach ball. But if we were to tilt it, let's see what happens. Bernoulli's principle only works so well in terms of levitation. If we tilt the leaf blower too far to the side, right, we just use it as kind of a directional force on the beach ball. I see a couple more questions. So before we move on to our very last demonstration, let's answer a couple of your questions. Does cutting down trees lose air? No. So cutting down trees doesn't make us lose any air. What we lose when we cut down trees is those trees are what give us oxygen back. So they're actually able to take in carbon dioxide from the atmosphere, go through their chemical process, and expel it back as oxygen. So even though cutting down the tree doesn't remove any volume of air, it takes away our ability to turn the air around us back into oxygen, which humans need to breathe. Great question, Jennifer. Yeah, so air pressure does matter. I see that in the comments too. All right, so we've got one final demonstration using or talking about air. Now, we said that air composition here on Earth is very, very unique, but the composition of air or the composition of other planets and other celestial objects is not the same that we experience here on Earth. We're going to talk about this in terms of this graph right here. So this graph right here shows us the elemental composition of the air that we breathe, the air inside Earth's atmosphere. Now, if you've stuck around for Echo Live for a while now, you might remember our liquid nitrogen show. Now, nitrogen as a gas is all around us. It makes up about 80% of the air we breathe, about 78.08%. Oxygen, which we said is important for human life, and even for combustion, makes up about 20%, or almost 21% of our atmosphere. Now, the rest of the air is kind of microscopic traces, or very, very small traces of different elements. And one of those is hydrogen. So hydrogen does not make up 5% of the atmosphere. It's not 0.5% of the atmosphere. It's actually 0.0005% of the atmosphere. So a 5 with 4 zeros in front of it. So a very, very small amount of our atmosphere is made out of hydrogen. Now, if we look at the elemental composition of the sun, it's pretty different, right? Now, on the sun, hydrogen makes up about 90% of the sun. And so part of this, right, is why we can't live on the sun. Hydrogen is over 90% of the sun's composition. Not so great for human life, right, because you can see that oxygen is now 0.07% of the sun. We wouldn't be able to breathe there. And additionally, right, the sun is a big fireball. So not so great for human life. But I do have some hydrogen here inside my studio. Now I've put my hydrogen inside this ball, which you might recognize. Now this is a different one. I have labeled it, so I've put a label on the top that this one is not full of my breath. It's not full of the air from around us, even though this one is also Jupiter. You can see the big red spot. I've actually filled this beach ball entirely with hydrogen. So hydrogen gas here inside the beach ball, and we're going to use it for a demonstration on creating a fireball right here inside the studio. Now, since we're going to create a fireball, right, we have to take a couple safety precautions. So I've come prepared. I've got a pair of safety goggles. I'm going to put my hair back behind me. Since we're working with fire, it's super important to always be safe. So I'll tie my hair back. As always, when we're working with fire, right, we also need this very important piece of equipment, our fire extinguisher. Even though we don't expect to need to use it, It's here just in case we were to have a need for it. So we're always going to be safe and always going to be prepared. What we're going to do is we're going to create hydrogen bubbles here inside this container of soapy water. So we're going to squeeze our beach ball, creating a pile of hydrogen bubbles, and we'll use that to talk about density. Hydrogen makes a great fuel for combustion, and in combination with oxygen, which is in the air all around us, which acts as an accelerant, we can actually turn this into a pretty cool fireball that I'll get to hold in the palm of my hand. So we're going to go ahead and we'll squeeze our beach ball here. Create a nice big pile of soap bubbles, but these again are not full of air like we might create by just swishing the water around. These are hydrogen bubbles and are going to be highly, highly flammable. Now the last step for safety is to insulate my arm. So what we're going to do is I'm actually just going to dip my arm down inside, really coat my arm here with this nice cold soapy water. It's going to act as an insulator if you think back to our Kaboom Mystery show. So my arm is nice and insulated from the flame. Dry off my other hand here. We're going to scoop up our hydrogen bubbles. And here we go with our final air demonstration in 3, 2, 1. Thank you everyone so much for joining us here on Echo Live today. Let me dry off my arms. We'll hold for just a couple more questions. So if you've got more questions, please send them in the chat now. Now is a great time to talk about those. I do see one that says, what makes hydrogen? Hydrogen is all around us. It's actually one of the elements that formed our entire universe. So we don't make hydrogen, it just exists. But we are able to purify it or pull it out of the air in order to kind of trap it for use in science demonstrations like this. Let's see, let's check our Zoom chat. Let's make sure we're keeping an eye on our Facebook chat. Go ahead, keep typing your questions in there. Keep an eye on that. Again, this is a great time to thank our sponsors, like the DTE Energy Foundation, for their support of Echo Live. It's because of them and because of donors to the Science Center, people like you who are enjoying these programs, watching them from home, who are donating to the Michigan Science Center. It's because of all of you that we are able to host these programs for free every weekday. So thank you to our sponsors. Let's check back on our chat. A lot of people telling us how much they love science. And air does have weight. So anything that is made of matter, right, is made of atoms which have weight. Hydrogen is the lightest atom. It is number 1 on our periodic table. So different atoms do in different compositions of air have different weights. A couple people asked, how much air do we breathe each day? And that depends on the person. I would say that here during the studio, I get a little out of breath the more I talk and the more exciting demonstrations I do. But it's different. It depends on the size of your lungs, right? Because children's lungs are smaller than adult lungs. Male lungs are usually larger than female lungs. And so that really depends on the person. You could try an experiment at home where if you maybe count how many breaths you take in a minute when you're at rest, when you're relaxed, and you can multiply that by the tidal volume of the adult lungs, which is 500 milliliters. So count how many breaths in 1 minute, multiply that out to how many minutes are in a day, and then multiply that by 500 milliliters. And it's going to be a really, really large number to know how much air you inhale and exhale every single day. Let's see. A couple people asking, did it hurt? No. Since hydrogen is so light, right, as soon as I ignited those bubbles, they kind of lifted. And so my hand was nice and insulated from the flame. I didn't feel it at all. This water's nice and cold, nice and soapy, which trapped those bubbles inside until they were ready to be ignited. So didn't hurt. I see a couple of requests, can we do it one more time? And I say, why not? We've got some hydrogen left in here, so let's go ahead, make a couple more piles of soapy bubbles. Already got my safety gear on, so what's the harm, right? All right, we've got our hydrogen bubbles here inside our container. I need to re-wet my arm, re-insulate myself from the flame, just to be nice and safe. All right, so my arm is nice and wet, nice cold water. We've got a big scoop of hydrogen bubbles here in our very last fireball of the day. 3, 2, 1. All right. Thank you everyone so much for joining us. Again, we love bringing these programs to you at 2:30 p.m. Every weekday, 2:30 p.m. Eastern. If you would like to share this video on your Facebook page for anyone else who you think might be interested in watching, we would love that. Make sure you like the Michigan Science Center Facebook page. Make sure you follow the Michigan Science Center's Facebook page so you are notified when our shows do start. And we will see you all tomorrow for our very last Echo Live program of the week. Bye, guys.